Hello, and welcome to this presentation, Understanding Velocity Factor. In this presentation, we'll provide a brief overview of velocity factor and the two most common methods used to measure the velocity factor of coaxial cables. One of the ways of measuring a cable's velocity factor is using a vector network analyzer in distance default mode. We'll describe the basics of distance default measurements in this presentation, but please see the separate presentation, Understanding VNA's distance default measurements, if you'd like a more detailed explanation of distance default. As you should already know, electrical signals propagate at the speed of light in a vacuum, but this speed is reduced when signals travel through matter. Coaxial cable, or coax, is the most common way of conducting radio frequency signals, particularly when longer distances are involved. For some applications and measurements, it's important to know the speed of propagation through a given coaxial cable, and the speed is normally quantified as the cable's velocity factor. Coaxial cables consist of an inner conductor, an outer conductor, and an insulating or dielectric material between them. The velocity factor of a coaxial cable is a function of that cable's dielectric constant, epsilon, and is independent of the frequency of the signal carried by the cable. Velocity factor is normally expressed as a fraction of the speed of light, and therefore is a unitless quantity between 0 and 1. Note that you may sometimes see velocity factor specified as a percentage as well. Most coaxial cables have a velocity factor between about 0.65 and 0.82, although in some cases you may see cables with a velocity factor as low as 0.5 or as high as 0.9. As mentioned a few moments ago, velocity factor is important for many different applications, and these include distance default measurements, tuning stubs, phase matching, navigational and direction finding systems, etc. There are three common methods for determining velocity factor. These are reading the value from a datasheet, measuring round-trip time using a function generator and an oscilloscope, and using a vector network analyzer in distance default mode. We'll spend the remainder of this presentation giving a short overview of each of these methods. Many coaxial cables have their cable type printed directly on them, and this can be used to look up the cable's velocity factor from the datasheet. Here we have a nominal velocity factor of 0.84 for times microwave LMR 400 Ultraflex. Although the information is somewhat redundant, this same information is often given as a time delay in nanoseconds per meter or foot. Light moves at about 1 nanosecond per foot in a vacuum. It should be noted that the accuracy or tolerance for velocity factor is not normally specified in a datasheet, and the variation between the nominal or specified velocity factor and the actual velocity factor of a cable is typically on the order of 5 to 10%. This variation tends to be greater for lower-cost cables. Therefore, in applications that require high accuracy, measurement of a cable's velocity factor is recommended. The first of these measurement methods involves using an oscilloscope and a function generator, which can be either an internal generator, as shown here, or an external generator. If we know the length of a cable by physically measuring it, then we can determine a velocity factor by measuring the time it takes for a signal to propagate down the cable and back. The end of the cable is left unterminated so that our stimulus signal will be reflected by the far end. We use the function generator to generate a short pulse with a fast rise time, and an oscilloscope channel is configured to capture both the transmitted pulse and the reflected pulse. The time difference between them is then measured. Let's look at this procedure in a bit more detail. Here we see the oscilloscope capture, showing both the transmitted pulse as well as the reflected pulse. Note that the scope's time base will need to be on the order of nanoseconds or low microseconds for most cable lengths. Markers are used to find the round-trip time as shown, and the one-way time is simply half of this round-trip time. Velocity factor can then be calculated using the measured cable length and this formula, where c is the speed of light in meters per second. For example, if our measured cable length were 3.75 meters, and the round-trip time were 37.8 nanoseconds, then the velocity factor would be 0.66. Another common method for measuring velocity factor is using a vector network analyzer, or VNA, to make a so-called distance default measurement. The VNA sends signals into the cable to determine the distance to faults, which are points at which impedance changes cause signal reflections. The velocity factor of the cable must be known in order to make accurate distance default measurements. Conversely, if cable length is known, a distance default measurement can be used to determine the velocity factor of a cable, and this is done by creating a large fault at the end of the cable. Let's look at how this is done. Leaving the end of a cable open or unterminated will cause all of the transmitted signal to be reflected from this point back towards the source. When making a DTF measurement, this will produce a large fault or spike on a plot of return loss versus distance, as seen on the right side of the graph below. The velocity factor of this cable is determined by placing a marker at the known or measured physical length of the cable. If we start with a velocity factor of 1, this marker will always be to the left of our end of cable fault. We then change the velocity factor until the marker is on the end of the cable return loss peak. At this point, the length measured by distance default and the physical length will be the same, indicating that we are using the correct velocity factor for the cable under test. Let's end with a brief summary. The speed at which signals propagate in coaxial cables is normally quantified in the form of velocity factor, which is the speed as a fraction or percentage of the speed of light. There are three main ways to determine a cable's velocity factor. The first is simply reading the cable type printed on the cable and then looking up the value in a datasheet. This is not a measurement, but is sufficient for many applications. One way of measuring velocity factor is using an oscilloscope to measure round-trip time in a cable of known or measured physical length. This involves generating a pulse and then measuring the difference between the transmit and receive times when the pulse is returned from the end of an unterminated cable. Another common method is using a vector network analyzer, or VNA, in distance default mode. Here, the unterminated end of the cable will appear as a large fault, and velocity factor is then varied until the measured physical length and the DTF measured fault at the end of the cable coincide. This concludes our presentation, Understanding Velocity Factor. If you'd like to learn more about cable measurements, oscilloscopes, VNAs, or other related test and measurement topics, please see the links in the video description. Thanks for watching.